About alkene configuration and cis versus trans, E versus Z. And we're going to continue to talk about alkene configuration in the context of a subject that touches most anything you eat nowadays, and that is triglycerides, or fats and oils. So I think you've seen the structure of a triglyceride before when we talked about esters. Triglycerides are what we're talking about when we say fats or oils. Fats come from animals, oils come from plants, I think is the basic dividing line between the two. Seems like I'm just about to get a little bit of audio feedback. All right. Yeah, I'm recording. Okay. So a triglyceride is a triester. It's got an alcohol portion with 3 carbons and 3 oxygens, one attached to each of those carbons. And then each of those oxygens is involved in an ester bond with a long chain, what's called a long chain fatty acid. I will just draw one of these. So we'll just draw an 18 carbon chain, 2, 4, 6, 8, 10, 12, 14, 18. This portion, this acyl portion, sorry, I'm struggling to highlight it. There we go, close enough. This acyl portion is called the fatty acid. It comes just like in esters, we've talked about the alcohol segment and the acyl or carboxylic acid segment. This is the fatty acid segment of a triglyceride. In orange is the glycerol segment. And this is sometimes called glycerin. So each triglyceride has 3 fatty acids. And they don't all have to be the same thing. They can vary in length, and they can vary in composition. It turns out that the length of the fatty acid determines whether the triglyceride is a liquid, as is the case for these vegetable oils, or a solid, as is the case for animal fats and coconut oil. And we're going to talk about why that is, but first let me just introduce you to the main players among the fatty acids. So a fatty acid molecule by itself would look like this. So if this 18 carbon fatty acid were hydrolyzed, or if the ester bond broke, what you would get on the right-hand side is 2, 4, 6, 8, 10, 12, 14, 16, 18 is an 18 carbon carboxylic acid. Now you tell me at pH 7, what form should that adopt? The pKa of a carboxylic acid is around 4. So if pH is 7, is that proton still there? Nope, it's gone. The solvent water removes the proton, and you end up with the carboxylate. So this is the form, the fatty acid carboxylate is the form that fatty acids adopt. They have a group at the beginning that's somewhat polar, and we'll talk about what that means probably tomorrow. And then they have a long hydrocarbon chain, which is relatively nonpolar. And that's important for reasons that we'll talk about tomorrow. But what other fatty acids are available? You can divide them up into categories of saturated versus unsaturated. So what I'm going to do is I won't draw each of these, but for each fatty acid, we're going to make kind of a table. These are not numbers to memorize, but they are trends to understand. We're going to write number of carbons. Saturated here means no double bonds, no pi bonds. Okay? So a saturated fatty acid, what I've drawn here is an 18 carbon saturated fatty acid. it's got no double bonds in the hydrocarbon chain. That's what we mean by saturated. Unsaturated fatty acids will have double bonds in the hydrocarbon chain. So for example, and I'm just going to write a number of carbons, and then I'll show you the melting point of the fatty acid. The melting point is how high you have to turn up the temperature before the solid fatty acid becomes a liquid. You can see, for example, well, anyway, and we'll talk about what this has to do with triglycerides, but right now we're focused on the fatty acid. If it just had 12 carbons, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's carbon 12. This is carbon 18. Then the melting point would be 43 degrees Celsius. So if you've lived in the United States your whole life and you haven't been elsewhere, you are used to temperatures in Fahrenheit. Body temperature, 98 degrees, is about 37 Celsius. So 43 is a really, really hot day. This would be a solid even over 100 degrees Fahrenheit, right? If you do 16 carbons, it's a solid even at much higher temperatures. You have to turn up the temperature even more. If it's 18 carbons, it's 69 degrees Celsius. If it's 20 carbons, it's 77 Celsius. You can see that the more carbons we add, the higher the melting point is. Now we're not going to explain that observation today, but you should look at it as an observation that we're going to try to rationalize next time. The more carbons that are in this chain, for the fatty acid at least, the higher you have to increase the temperature for the fatty acid to become a liquid. And in general, if you look at a triglyceride, it is mostly fatty acid. And so the properties of the triglyceride are going to mirror, the melting point of the triglyceride is going to mirror the melting points of the fatty acids. All right? So now let's look at some of the unsaturated fatty acids. We're just going to do a few of these. The 16 carbon fatty acid, and here I'm going to write number of carbons, and then I'm going to write here a column for basically number and location of double bonds, and then melting point. So notice that the fully saturated fatty acid melted at 63 C. Same number of carbons, I introduce one double bond at position 9. Let's see if we can redraw that one. That's carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Then a cis double bond between 9, 10, 11, 12, 13, 14, 15, 16. So this is that 16 carbon fatty acid. One double bond. Now it melts at 0 C. So that's pretty dramatic. We didn't change the structure much, but boom, it became a liquid instead of a solid. One double bond will do that. If you go look at the 18 carbon fatty acids, you have a similar trend. For example, 18 carbons with a single double bond will, the melting temperature lowers from 69 C to 13 C. Notice we still get an increase when we add more carbons. We keep the double bond in the same place, but we add more carbons. Melting temperature increases, but the effect of changing whether or not you have a double bond, boom, lowers the melting point dramatically. And as you add additional double bonds, the effect gets bigger. So if I put in a second double bond that has the Z configuration between carbons 12 and 13, it now is a liquid below the freezing point of water. And if I add a third, we get down to minus 16 C. Okay. And then just for completeness, let me show you a 20 carbon multiple unsaturated fatty acids that has double bonds at 5, 8, 11, and 5, 8, 12, and No, I was right the first time. 5, 8, 11, and 15. This one melts at minus 50. So what a swing, right? From plus 77 to minus 50 just by introducing 4 double bonds. Yeah?
Hypothetically, if we were to start messing around with the melting point, do we figure out, if we don't already do this enough, do we figure out what kind of chain the saturated fat has based on the temperatures?
So could you hypothetically, if you didn't know the composition of the fatty acid, use a melting point to guess are there any double bonds present? Sure. I mean, it would be, though, it would be tricky because there's lots of variables. For example, the carboxylic acids that are shorter than this start to become liquid. So if something was a liquid, you wouldn't necessarily know, is it a liquid because it has fewer carbons, or is it a liquid because it has lots of carbons but lots of double bonds? But if you were told the number of carbons and you knew this information, you could probably figure it out. Unsaturated fatty acids tend to be liquids at room temperature. Saturated fatty acids tend to be solids at room temperature. So let's talk about some triglycerides. This is, I should have brought my reading glasses, canola oil. All right. That's just triglycerides isolated from canola seed. What do you think this has more of, saturated or unsaturated fatty acids? Unsaturated. Why? Because it's a liquid, right? And so the same is true for, let's see, what is this? Soybean oil, okay? Or peanut oil. All of them liquids at room temperature. You would predict more unsaturated fatty acids. Coconut oil, what do you observe here? Solid, yeah. Now if I held on to this, if I put it in warm water, I could get it to, if I soaked the jar in warm water, warmed it up a little bit, I could get it to melt and become an oil. But it's a solid. So what's your prediction? Fatty acid composition of coconut oil? More saturated. Okay, so we can actually look at this and see I'll write down the fatty acid composition of various oil sources, and you can see that the overall properties of the triglyceride mirror what you would expect from the fatty acids that are there. For example, if we write down animal fat, and of course this is going to vary depending on which animal you use. Let's suppose it's beef tallow, or maybe it's pig fat, lard. Down in South Texas on my mission, you could go to the H-E-B and buy great 5-gallon buckets of manteca to make tamales. It was really, really good, but animal fat, and if we write up here, sort of saturated fatty acids and unsaturated fatty acids, and we're going to write, let's see why I'm doing this. Yeah, let's write number of carbons here. We'll go 14, 16, and 18. And then for the unsaturated fatty acids, we're going to focus, and there's more that are present in these triglycerides, but what I'm showing you here, let's write the 18 carbon one with a single double bond, and then the 18 carbon fatty acid with 2 double bonds. One of these is called oleic acid. The 1 double bond is called oleic acid. The 2 double bonds are called linoleic acid. 3 double bonds, like you saw in your quiz, is called linolenic acid. So for animal fat, it's a lot of, it's 1% 14 carbon fatty acids saturated, 25% 16, and 15% 18. Got about 50% unsaturated 9Z and about 6% polyunsaturated 9Z, 12Z. So having, somewhere between 25 and 40% saturated fatty acids is enough for a triglyceride to be solid. Let's do olive oil, which a lot of people like. It's got only a much smaller composition of saturated fatty acids, and it's 80% monounsaturated and about 7% diunsaturated. I know these numbers don't add up to 100. That's because it's not a complete list. If we wrote peanut oil, it would be very similar. peanut oil, and I think this is true of nuts in general, are richer in polyunsaturated fatty acids and other things. So 20% of the diunsaturated one. And then let's look at coconut oil. As expected, and the data I have didn't break it down per fatty acid, I just have a number here, 86% in the range of saturated and only 7% in the range of unsaturated. Okay? So when you read on food labels about saturated versus unsaturated fats, this is exactly what it's talking about. And when you look in the baking section and you see the various oils that are available to you, you can tell whether they're liquid or solid. That tells you whether they're full of mostly saturated fatty acids or not. Okay? Questions about that? Okay, who cares is an interesting question. So, have you ever eaten anything that has gone rancid before? What do I mean when I say something has gone rancid? I'm not really talking about generally rotten food. We're not talking about moldiness or like you're not smelling rotting flesh or putrescine like we talked about. When something is rancid, what does it taste like? It just tastes expired and maybe a little bit sour, right? So there was a time, I brought these tostadas here today. I bought them several years ago. So if you want to taste rancid tostadas, you could probably do it. Somebody asked me if they could do it last time I taught a class about this, and I was like, I don't really think I want to be held responsible for what would happen. But if you want to smell, you can even smell the rancidity. It smells a little bit stale, and what has happened to those is the unsaturated fats in it reacted with oxygen. So I can tell you what kind of oil's in this. Actually, maybe I can't. Can I? Oh, it'll happen to you too someday. Vegetable oil, palm olein. Okay, so it's got palm oil, some saturated and unsaturated fatty acids in it. You learned that alkenes, what is the HOMO of an alkene? The pi double bond, right? So if you were looking for an alkene to be a nucleophile, the carbon-carbon pi bond is a reactive set of electrons, right? The carbon-carbon pi bond reactivity, and I won't show you the actual reaction because it relies on some chemistry we haven't talked about yet. But carbon-carbon pi bond reactivity with molecular oxygen results in the rancid taste of expired oil. Literally, you end up adding some oxygens to the atoms immediately adjacent to the pi bond. And again, the specific chemistry there isn't important, but as good as unsaturated fatty acids, or as good as unsaturated triglycerides composed of unsaturated fats tend to have better health outcomes, they're not as shelf stable as if they were saturated fatty acids. Go ahead.
Oh, I was just going to say, is that why hydrogenation improves the shelf life?
That's exactly right. So,
Makes it that the pi bond can't bond with anything else.
yeah. So let's talk about that. How many of you have heard of hydrogenation of fats and oils? If you've been in food science, maybe you have. The word hydrogenation refers to a chemical reaction. So let's just say over time, with the presence of oxygen, that double bond, some of the carbons nearby that double bond can get oxidized. They can get functional groups like that adjacent to the pi bond, and that doesn't taste the same, and it doesn't smell the same. And that reaction doesn't happen if the pi bond isn't there. So one of the strategies for preventing this from happening is to do a reduction reaction in which you add hydrogen, or H2, across the double bond. So you basically are going to, in this reaction, I'm going to replace the hydrogen-hydrogen sigma bond and the carbon-carbon pi bond with two new carbon-hydrogen sigma bonds. So let me draw that for you. The pi bond will be gone, and in its place on carbons 9 and 10, carbons 9 and 10 already had one hydrogen each. Now they have two hydrogens each. These are the new hydrogens that were added, and the electrons for those bonds come from the pi bond and the hydrogen-hydrogen sigma bond. This reaction happens in the presence of the metal palladium. This is a palladium catalyst. It's usually immobilized on charcoal or carbon. So we'll represent that with PD and a slash called C. This is what we call a hydrogenation reaction. And this gets rid of the double bond. Now, what is the prediction there? If you hydrogenate, what is that going to do to the melting point of the fatty acid? Should go up, right? And is that a quiz question or is that on the problem set? The unsaturated fatty acid should have a lower melting point. The saturated fatty acid should have a higher melting point, but it is more shelf stable. It lacks the double bond, so it can't do the rancidity reaction. So to prevent the double bond from reacting, we do this hydrogenation reaction, which is an example of a reduction reaction. The word reduction is important in organic chemistry. Reduction of a molecule leads to an increase in the number of carbon-hydrogen bonds and or, sometimes at the same time, a decrease in the number of carbon heteroatom bonds. I'm going to just say Z is any heteroatom, like nitrogen, oxygen, halides, sulfur. Okay, so this is a reduction reaction because you took the alkene, which had carbons 9 and 10 only had one CH bond each, and then you become the alkane where carbons 9 and 10 each have two CH bonds. An increase in the number of CH bonds is a reduction reaction. Okay, so if you did this to a triglyceride, if you took vegetable oil, like this stuff, pure vegetable oil from Crisco, and you hydrogenated and reduced all the double bonds to alkenes, how should the properties of this change?
Solid.
Become solid. You ever bought Crisco in the solid in the jar? It's this white solid that's really greasy. That's just this stuff, and it's been hydrogenated. Okay? And they do that for increased shelf stability. They also do that because sometimes you don't want your oils to be liquids. So another example of that is this lovely, and again, I wouldn't recommend tasting this as I bought this years ago. This is Adam's 100% natural peanut butter, creamy. And you can see, I don't know if you're looking at that, you can see there's a lot of oil at the top. Now some of you may like natural peanut butter. Anybody ever opened it up and drank the oil? No? Extra credit? No. No. So when you want to eat this, what do you have to do? You have to stir it up because the oil separates out. The oil's less dense than the solids. The oil separates out because it's a liquid. Now, here is Skippy peanut butter, and Skippy is a solid. If we open this up, oil would not drip out of Skippy. Why is that? It must have fewer unsaturated fatty acids in its triglycerides. And in fact, if you read the label, roasted peanuts, hydrogenated vegetable oil. Hydrogenated vegetable oil. That means they took this, actually it was cottonseed oil and soybean soybean oil. Why they didn't use peanut oil, I don't know. It's peanut butter. Anyway, they took this, they hydrogenated it to a solid, they mixed it with this, and now the oil doesn't separate out. And this will be more shelf stable than this. You can probably open this up, expose it to oxygen for longer than this one, because the double bonds here aren't going to be that reactive. Now let's talk a little bit about that hydrogenation process, because depending on how you run it, hydrogenation can be reversible. Meaning the reaction can go backward. Now, and I'll just say partial hydrogenation. So if you really want to force the reaction to make it go 100%, you just provide a huge excess of hydrogen. Use Le Chatelier's principle, add a huge excess of hydrogen, the reaction goes forward, you're done. But suppose you didn't want to do that. Suppose you wanted to just partially hydrogenate. Maybe for whatever food purposes or taste and mixture you want a lot of the double bonds to be gone, but not all of them. If it's incomplete, when you start the reaction, I'm just going to zoom in on the part of the reaction that, the part of the molecule that's cis, as this is the 9Z double bond. This is our starting point. When you reduce with hydrogen and palladium on carbon, you lose the double bond, and now you're free to rotate around that single bond. And if it goes backwards, you have the possibility to not only get the cis configuration, but also the trans configuration. And the problem with that is that the trans configuration is not ever found in nature. Natural vegetable oils don't have trans double bonds. Okay? So if you've heard about trans fats, have you heard about that before? People have told you. The most common context, I think, is it's now on food labels. Trans fat free. As though that's some particular benefit. All food should have been trans fat free until they did something to it and then introduced the trans fat. So when they say trans fat free, what they mean is either they completely hydrogenated or they didn't hydrogenate at all. But partial hydrogenation should have some trans fats in there. Now, what's the deal with trans fats? What have you heard?
They can increase LDL, which is
Right. If you search, and again, it's hard to search nutritional information. I just encourage you as you're searching things to get information from reliable sources. Some person on Instagram, no matter how many followers they have, does not mean that they have access to truth. And there's a lot of crazy things going around nowadays. PubMed, run by the National Institutes of Health, is a pretty good place for reliable information. What I was able to find is just that, like you said, trans fats are associated with higher LDL, which is bad cholesterol. That's the lipoprotein particle that carries fatty acids and delivers cholesterol to cells. And if there's too many of them, you can start to get plaque buildup in your arteries and start getting atherosclerosis. So the exact connection between those two events, I wasn't able to find a biochemical mechanism. I don't know why it's associated, but it is. And that's why food companies are falling all over themselves to say this product is trans fat free, because American consumer scared of trans fats, our product's trans fat free, yay, we're happy. Now, go ahead.
Does it get the bond with the oxygen?
Say,
How does it get the double bond?
how does it get the double bond back? The catalyst is able to interact with the CH bonds. This is a reaction we're not really going to learn about in any level of detail. But the catalyst basically takes one of these CH bonds and one of the hydrogens and the other hydrogen and makes hydrogen gas, and then takes that set of electrons and makes the new pi bond. So it's running the first reaction backwards. I don't actually know how it works. It's a good question, but yeah. So if you read partially hydrogenated vegetable oil on a food label, that's somewhere where there might be the possibility of trans fats. Go ahead.
Is that trans
Yeah, is that trans configuration when it goes backwards likely to be more likely because it's more stable? Yeah. Now, I think the FDA guidelines are you can claim to be trans fat free as long as you have less than some value of trans fats. I think it's like 500 milligrams, which is actually a decent amount. But so anyway, that's the story with trans fats. And so partial hydrogenation is something that people are careful about now. And if a food is declared to be trans fat free, that means they've somehow minimized this going back to the trans, or perhaps they've fully hydrogenated. Okay. All right. Let's see. There's one other thing. Oh, omega-3 fatty acids. Have you heard about those? Okay. So linolenic acid that was in your quiz, I'm just going to erase all the things that we did. I'll put all of that back. This is an example of, it's a polyunsaturated fatty acid. It has multiple double bonds. This is an example of what we call an omega-3 fatty acid. And the reason we call it an omega-3 fatty acid is when chains are really long, I told you before that we'll start, here's the carbonyl carbon, the one that's bonded to a carboxylic acid. This is the alpha carbon. We could continue to assign Greek letters from there, but eventually we forget them. And so what we do is we go to the end of the chain and we say, that is the omega carbon. Okay? That is omega carbon 1, omega carbon 2, and omega carbon 3. Omega-3 fatty acids have a double bond, a cis double bond, on the third carbon from the end. Counting inward, starting with 1 on the last carbon. The last carbon's omega-1, then the next one's omega-2, then the next one's omega-3. So omega-3 fatty acids have that double bond in that position. What's the big deal with them? What have you heard? There's a lot of potential claims. It's supposed to be good for you. You can now buy eggs that are enriched in omega-3 fatty acids. All they're doing is feeding the chickens stuff that has omega-3 fatty acids in them. The evidence suggests there was a large meta-analysis of various things in 2021 that suggested that omega-3 fatty acids reduce cardiovascular mortality and improving outcomes. However, people have argued for a lot of other things like anti-cancer, anti-Alzheimer's, and there's limited evidence for that. So the evidence for cardiovascular improvement is good. The other claims need to be investigated more. All right, next time we're going to talk about more properties of fatty acids. We're going to do an experiment with oil and water and an egg. I really wanted to do this today, but we've run out of time. So hopefully the egg will keep. I'll see you tomorrow.